Okay, moving forward. So I want to describe the application of electron waves. Okay, so excuse me, before I describe the application, I'm going to describe more about electron waves. So de Broglie, very famous quantum mechanicist, a very young man as well in the 1920s when he came up with this equation. If electromagnetic radiation, so that's light, right? If electromagnetic radiation behaves as a particle, could a particle in motion, such as an electron, behave as a wave? And as it turns out, the answer is yes. There are loads of very cool examples of this. Okay, so here's our famous de Broglie wavelength equation. The de Broglie wavelength equals h divided by p. We recall that's p for momentum, which equals mass times velocity. Okay, and of course h is Planck's constant. So I'm going to write that h divided by p. I also want to write another representation of momentum, probably something that you're not used to seeing, and that's going to come back later on. Okay, so I'll remind you that kinetic energy, I'm going to write that Ke, right? We know that's 1/2 mv squared. Well, there's another way I can write this equation with respect to momentum. Okay, and I'm not going to do the algebra. I'm just going to present that to you directly. Okay, so kinetic energy can also be written as p squared divided by 2 times mass. Okay, and so I can, well, I lied. I'll prove that to you right now. So we know, I'll prove it to you backwards. So we know p squared is going to be m squared times v squared divided by 2m. And so you can see this quite easily, right? An m and an m cancel, and we have 1/2 mv squared. So it's not that hard of a proof. So I'm going to come back to this momentarily, that kinetic energy, 1/2 mv squared, but also can be p squared divided by 2m. So I'm going to show you a cool experiment, the Davidson-Germer experiment, that scattered an electron beam from a nickel crystal. Okay, and I'm going to show you where this gets its application, or where the application of this experiment. So an electron beam is fired at this nickel crystal, this nickel solid, very similar to how the photoelectric effect experiment is done, except for instead of electron beam, it's a light beam in the photoelectric effect. Okay, in the Davidson-Germer experiment, this is an electron beam. So the electrons scatter off of this surface. They are diffracted, and what's observed, if you put an observer right here, okay, so I'm going to draw this a lot, like a little kind of weird looking eyeball, like the side view profile of an eyeball. That would be an observer. An interference pattern is observed between these diffracted electrons. We note that as a diffraction pattern, but it is interference. It is constructive and destructive. Okay. So I'll remind you, diffraction is the change in directions of waves when they pass through a small opening or around a barrier in their path. So this leads to either a collimated beam or a divergent beam, as mentioned earlier. So there is much less diffraction when the length of the opening is greater than the wavelength. But if we narrow the opening, there's a lot more diffraction. Okay? And so now what we have to consider with this electron beam phenomenon, okay, these openings, or excuse me, with the Davidson-Germer experiment, okay, these openings are related to the space between atoms in a crystal lattice. Okay? Which is very cool. This is exactly then what has led to electron microscopy. Application of electrons acting as waves. One of. Okay? So SEM is scanning electron microscopy, and TEM is transmission electron microscopy. So I know the font on this thing is really small here, so I apologize about that. But you can see what's going on here. I'll describe this. So here is our, I'm just going to call it the Electron Gun, commonly referred to in laboratories. Okay, so there's the Electron Gun, and here's also the Electron Gun. Here is the anode, which is a positively charged plate, and that attracts the electrons very divergent, as you can see. Okay, but now what happens? A series of what we call electron optics. Electron optics. Get out of here, Siri. I didn't ask for your help. They're listening to me. Jeez. Okay, so electron optics. Sometimes these are called Einzel lenses. There's lots of German influence in this field, as we shall see. Electron optics or Einzel lenses, they function to converge and eventually collimate our electron beam, which is very cool. And so in scanning electron microscopy, here the sample is way down at the bottom and it's on a platform that can scan, right? Okay. So most notably, SEM is very useful for, taking a picture of like a bug or some very small critter, because you want to get a picture of the whole thing, so you're scanning it around. Okay, and so there are detectors right here that then detect those scattered electron beams. Okay, in transmission electron microscopy, our sample holder is way up here. Okay, so you can see this electron beam will actually transmit through the sample. It transmits through the space between atoms, which gives us a diffraction pattern, okay? Which is very cool. And then that diffraction pattern is shot onto a phosphorus screen, and lots of complicated math is used to convert that diffraction pattern into an image. And often that image is atomically resolved. So we get atomic scale, which is awesome. Okay. So now what I want to walk you through. Okay. So there is a potential difference in the SEM and the TEM, and I'm going to represent that as, I'm going to follow the, I'm just going to write it as delta V for voltage. Okay, so there will be a potential voltage difference between the anode and the electron gun. That allows the electrons to accelerate through. And I'm going to back up and I'm going to go to this de Broglie wavelength here. Okay, so we can represent, I'm just checking my notes here momentarily. All right, so we know if that delta V, so I'm backing up on this equation here to show you how the de Broglie wavelength equation can be used in electron microscopy. So we know delta V is in units of volts, which we know from our previous lecture is a joule per coulomb, okay? And if I multiply this quantity times E delta V, where that E is fundamental charge, right? 1.60 something something times 10 to the minus 19 coulomb. If I take E, fundamental charge, times delta V, that's going to be a joule per coulomb times a coulomb to give me a joule. So in other words, E times delta V gives me the kinetic energy of those electrons. All right, very cool. And so, of course, what I can do is now set the kinetic energy equal to, we know it's equal to 1/2 mv squared, which is also equal to p squared divided by 2 times m, which we know is also equal to E times delta V. Okay? And now if we substitute for P, okay, that's what we want to solve for, right? We know P is going to be 2 times the mass, and now specifically this is mass of electron, okay? 2 times mass of electron times the charge of that electron times this potential difference, and because that's a square, that's all square root. So why is this useful? Well, I'm going to rewrite this equation. Sorry, I ran out of room here, okay? I'm going to rewrite the de Broglie wavelength equation as lambda B, lambda de Broglie. I suppose I should have wrote dB, but lambda B is fine. Equals H divided by the square root of 2MeE delta V. So why is that useful? Well, this is the equation that microscopists, and really microscopists don't even use this equation. The computer software controlling the microscope uses this equation. And it says, okay, that's the variable we can set in the microscope. And what that gives us is wavelengths. Our goal in using, excuse me, I'm blowing up on my Mac moves here. The goal of this is to find a voltage that will give us a de Broglie wavelength that is on par, that is in the same scale as the space between atoms, thus allowing the electron beam to transmit between the space of atoms and diffract and give us that diffraction pattern. Okay, so I'm going to ask you to use this equation in our first Mathematica assignment to do some calculations. Okay, so great. I think that is pretty good.